Okay, hello everyone. So today, day 28, we'll be talking about introduction to null hypothesis significance testing. All right, and so the goals, the objectives so this fits in after we've talked about descriptive statistics. And so it's nice to have this sort of floating day so that we can make reviews on Monday and Tuesday and the celebration of knowledge on Wednesday and Thursday. And so this one goes before the celebration of knowledge for one section and after it for another. And so the purpose of it is to prepare you for your final project, because you're going to need to conduct one of these hypotheses tests for your final project. Okay, so the objectives for today are to understand the basic setup for null hypothesis significance testing. And there are 14 different situations in which you will be able to apply this theory. And so we want to be familiar with those. And then we want to be able to identify the situation given a scenario. Okay, so a lot of this doesn't make sense yet, but these are the objectives for the end of the day. So hopefully by the end of this video, you'll have a clear idea of what those objectives entail. All right, so there's a basic setup to what is called a null hypothesis significance test. And this is the basic setup. First, you have a population parameter that you want to know about. Now, this is fairly common in research. You want to say something about not just a small group, but a whole population. All of the students at SVU, perhaps. However, generally speaking, population parameters are not accessible. You can't just go and query everybody in the population. That's certainly true for countrywide populations. Well, what do you do? Well, you make a guess. That's the second step. You make a guess about that population parameter. This is the null hypothesis. So it's something like mu, so this example here, the mean height is 66 inches. So we were saying mu equals 66 inches. Remember, mu is the population mean. Or the proportion of voters is 0.06. And so that is P equals 0.06. So I make a guess about my population parameter. The next thing to do is to take a sample and compute that corresponding statistic. And so you do that, you get something like X bar equals, some value. In this case, we get X bar equals 68 inches, and that was a sample of 30. And the question is it likely that the true population mean is 66 inches when I was able to get a sample, and these will have to be random samples, when I was able to get a sample and the average height was 68 inches. Now, the question is that a fluke? Is the difference between 66 and 68 explainable by the natural variation of a sample of 30 students? Or does it suggest that the true mean is actually not 66 inches? Making that determination is step 4. Test if your statistic is significant. Significant is a very loaded word. It's a big word there, conceptually speaking. Is significantly different from your guess. That's what we're going to be able to do in Unit 3. We're going to leverage modern probability theory to determine the likelihood of us getting data with such and such a statistic if the population parameter was as guessed. And if that likelihood is super low, we will reject our guessed population parameter. We'll reject that guess. Okay, now we will talk about the nitty-gritty later on. For now, what I want you to understand is the different situations in which this theory may apply. All right, let's go on. So we've got 14, please write this in, 14 different tests that we will learn about. Let's get going. The first one is a one population proportion. Okay, so this is just where you are comparing the proportion. 60%, 30% of the population of a single population. Okay, there's just one population. Against some value. I've got 3 examples here for you. The population of all SVU students who are registered to vote is greater than 0.60. So you're interested in the population to vote. You're wondering if it's greater than 60%. So implicit in that is a guess. You're going to guess that the population proportion is 60, and we're going to test to see whether that's accurate. Remember, your null hypothesis always has to be a value. You're guessing a value for that population parameter. This equation here, this mathematical representation of our guess at the population parameter is called the null hypothesis. Okay, what's another one? Is the population of all adults in the United States who've received at least one dose of the vaccine greater than 70%? All right, so the population is all adults in the United States. The variable, the parameter is the population. Is the population proportion, P, and we are guessing that P is equal to 0.70. Now, you always have to have equality for the null hypothesis. That's going to be our guess, and you'll see that we'll be able to answer this question as to whether the true population proportion is greater than that. You'll be able to see how we can answer that when we get into Unit 3. But for now, just know that this is a way of validating a guess for the population proportion of a single population. Okay, are the majority of registered voters in favor of a certain candidate? Again, this majority idea is a proportion, and the null hypothesis is going to be that proportion equals 0.5. And we'll be able to test whether or not the proportion is greater than 0.5, which is equivalent to there being a majority. Okay, so that was the first test. Second and third test have to do with population mean. All right, so this one we're interested in comparing the mean of a single, okay, so just one population, to some value. Now, there's 2 cases in this. One is the population standard deviation. I can't remember. And the other case is that you do not know the population standard deviation. Okay, so remember the population standard deviation is sigma. So if sigma is known, then that's test 2. If sigma is not known, there is different procedure, and that's test 3. All right, so examples. Is the IQ of students at SVU, is the mean, sorry, that's a very important word, is the mean IQ of students greater than 110? So the null hypothesis is going to be is mu, which is my average, the average IQ, I'm going to say, is that equal to 110? That'll be my null hypothesis, always equality. Is the mean weight of all students in college athletics greater than 175 pounds? So again, mu greater than equals 175 pounds. So that's my guess. Okay, now with this first one here, you may not know this, but IQ is contrived to have a population standard deviation of 15. So in this case, we do have a value for that population parameter. And so this is going to be test 2. This one here, there's no population parameter mentioned, and I can't think of a good population mean. So this one here will just be test 3, sigma not known. Okay, is the mean number of hours all college students study per week greater than 10? So again, we do not have, so this is mu equals 10 is our guess. This is a mean of a single population. That's just college students, all college students. That's our population. And again, there's no sigma in sight, not known. Is the mean number of minutes. Okay, so all of these questions fall into this category because there is a mean and there's a single population. Okay, now the next 5 tests all have to do with 2 populations. So here we are interested in comparing the proportions of 2 populations with each other. All right, so is the population of registered voters among SVU students greater than that of BYU? Have you ever wondered something like this? Maybe not with registered voters, but where you compare the proportions between 2 groups. All right, so this right here, you would have P1, maybe that would be the population proportion for SVU, and we're going to guess that they're equal, and we're going to see how that shakes out. But you've got 2 populations, and you're comparing their proportions. Here's another example. Is there a difference in the proportion of adults in the United States who have received at least 1 dose of the COVID vaccine per 2 states? Okay, so do 2 given states have the same vaccination rate or not? You could think, that if you wanted to test the effectiveness of messaging, then you could test to see whether, different states had the same, 2 different states had 2 very different types of messaging. Did it make a difference? And so you could test whether one state has a higher vaccination than the other. You could do that using this hypothesis test. This is test 4. Is the proportion of adult men with traffic violation less than that of adult women with traffic violation? So again, this is the proportion of adult men with traffic violations. Is that equal to the proportion of women? Your null hypothesis is always equality. Okay, next we've got, this is a set of 4 tests. Here, in each of these tests, we're interested in comparing means of 2 populations. Okay, so this actually has 4 cases. Test 5 is where both population standard deviations are known and equal. They are known and equal, so that means sigma 1 equals sigma 2. Test 6, both population standard deviations. Standard deviations is the thing that makes the difference here. You have to know about the standard deviation in order to determine what test is required. This one here is unknown. Oh, no, sorry. These are still known, but they're not equal. Known, but not equal. So sigma 1, you know it, does not equal sigma 2. Next is when both population standard deviations are unknown and assumed equal. So you don't know what they are, but you're assuming that they're equal. And then the last case is when the standard deviations are unknown and assumed equal. This one right here, test 7, is the most computationally difficult. So the computation of each of these tests is different because of this different, what we know and what we don't know. Okay, but so basically, if you have two populations and you're comparing their means, you're going to use a test 5 through 8. Okay, so here's some examples. Is the mean height of SVU students greater than that of BYU, assuming populations have standard deviations equal to national average? So this one here is, it's just, there's this one national average. So this is going to be test 5. There's sigma 1, sigma 2 are known and equal. They're both going to equal the same national average. Is the mean weight of college athletes greater than that of non-college athletes? So you've got pro athletes or other. Assuming unequal and unknown variances. Okay, now remember, variance is just the square of the standard deviation. So this is equivalent to saying unknown standard deviation. Unequal, unknown standard deviation. So this is test what? Test 8. Is the mean number of hours college students study per week greater than that of high school students, assuming both populations have unknown but equal standard deviation? So this is test 7, because the variances or the standard deviations are unknown but equal. That's test 7. Two populations, you've got college students and high schoolers, and the same variable. That's going to be the mean of the number of hours that they study. Okay, is the mean number of minutes college students spend on social media per day greater than that of high schoolers, assuming both populations have unknown unequal? So unknown unequal, that's test 8 again. Two populations, one variable, and you want to know the mean of that, the two population means of that variable. Okay, now, one other little test here. This is where, so in this example here, all right, these tests here, each sample that you will take will be independent. And the populations are somewhat independent as well. This next test, okay, this is test 9. You are interested in comparing the means of two populations that are related in some way. Example of that is there a difference in the mean test scores between before and after of students before and after taking a statistics course? So before is one population, after is another quote-unquote population. It's the same people, but there's something different about them, and so you could call it a different population. And so, however, though, they are related. They're related to each other. And so you couldn't do something over here because we assume that they're independent. But this one here, it's okay. Is there a difference between the mean blood pressure of patients who are husbands and that of their wives in a husband and wife study? Is there a difference in the mean time? Is there a difference in the mean time it takes to run a mile before and after a training program? So again, before and after, they're paired. Okay, the last few tests here, we've got just 3 more types of tests. So there's the chi-squared tests, and these you are interested in the distribution. So sort of think of the histogram, or since it's categorical data, it's not a histogram, it's a bar chart. So think about the frequency chart of a categorical variable. You want to know particular things about that. So a goodness of fit is the distribution of a single categorical variable. So think of the frequency chart. Is that distribution of a single population different from some expected distribution. Test 11 is called a test for independence. Is there an association or correlation between two categorical variables in a single population? What's that look like? We'll see an example in a minute. And then there's a test for homogeneity. This is asks, is the distribution of a single categorical variable the same across different populations? Okay, this is definitely a lot to take in and to sort out. We're going to take more examples of this. Is the distribution of, so you've got so many flavors of ice cream, right? You have vanilla, you've got chocolate, and maybe you've got other. Okay, just very simple. There's way more than that, of course, right? But suppose you only have a categorical variable with 3 categories, and this has some distribution among SVU students. So many like vanilla, so many like chocolate, so many like other. And you have a national average. Maybe Nielsen families surveyed, it got a national average or something like that. How do we compare with that average? Is ours statistically the same? I say statistically because it's not likely to be exactly the same, but is it close enough? Or is it statistically different? Is it significantly different? Is the distribution of political affiliations the same across different age groups? Okay, so back to the previous example, that's a goodness of fit. So that's test 7. That's test 10. Because it is one population, one variable compared with some expected distribution. Now what we have is the political affiliations. This is one variable across different age groups. So this one here is test 12. This is a test for homogeneity because it's one variable, different groups. Is the population of smokers and non-smokers the same between 2 similar companies? Between 2 similar companies. So this one is one variable, multiple populations. So this again is test 12. Now this previous one, you could think of it a little differently. Is the distribution of political... So you could think of political affiliation and age groups as 2 categorical variables. What age group somebody's in, that's a categorical variable. Their political affiliation, that's another categorical variable. And there's just one population of all these people of different age groups, different political affiliations, but it's all just one big group of people. And you want to kind of determine the distribution, whether or not these affiliations depend on age group or not. So you could also think of this one as being in step 11. One population, 2 categorical variables. Okay, now, the last 2 have to do with correlation, just like the test of independence. Okay, so here you are interested in whether there is a statistically significant linear relationship between 2 quantitative variables. Linear relationship meaning, there's a correlation like a line. All right, so is there a significant correlation between student hours and exam scores? Does one affect the other in a linear way, as a line? Is there a significant correlation between age and income among working adults? Okay, and is there a significant correlation between temperature and ice cream sales? So we'll be able to determine whether or not those things are true, or at least whether they have a linear correlation by the end of Unit 3. So all of these here are Test 13. And then lastly, Test 14, the very last test. Here you are interested in comparing the means of quantitative. The means of, if you have a mean, it's got to be quantitative. Variable across 3 or more populations. Or you could even think of this as categories of the same population. In the same population. So here's an example. Is there a difference in the mean test scores among students from different majors? Math, biology, history, all those different majors. You could see if there's a mean, and if there's a statistically significant difference in their mean. Is there a difference in the mean weight among athletes from different sports? So football, basketball, swimming. See, it's not just 2 like with the tests 5 through 8. It's many of them. Okay, and this takes a significantly different procedure, and we'll be evaluating test 14 using Python, but that won't be till the very end of the semester. Is there a difference in mean customer satisfaction ratings among different store locations of a retail chain? So one variable, this is the customer satisfaction. It's a quantitative one, 1, 2, 3, 4, 5. It's quantitative, but there's a bunch of different categories or populations. Okay. Now let's work on identifying the test. So here's some scenarios here that we want to work through. So we've got 14 tests, and we've got to identify which scenario goes with which one. All right, so let's get started. A university claims that the average time students spent studying per week is 15 hours. All right, so you've got this average. So students, there's just one population here, and they claim that they spend 15 hours. It's an average. A random sample of 40 students was selected. The population standard deviation of the weekly mean study, the population standard deviation of the study is known to be 4. Okay, so I've heard enough. This right here is going to be test 3. It's going to be it's a single population mean, so one population mean with known. This is going to be test 2. Known sigma. So that's test 2. Okay, a manufacturer states that 8% of its light bulbs are defective. I'm thinking a proportion here. A quality control inspector randomly selects 300 bulbs from the production line and finds that 34 are defective. The inspector wants to determine whether the true defect rate differs from the stated rate. All right, well, this right here is just test 1, because it is one population, proportion. That's it. That's test 1. One population, a single batch of, just the light bulbs, and a proportion, 8%, or the defect rate. A researcher wants to determine whether there is a linear relationship between students' final exam scores. Okay, a linear relationship. That cues to me that this is a test 13, which is correlation. There is a linear relationship between students' exam scores and the number of hours that they spend in tutoring sessions. All right, so this one here has exam scores and number of hours, 2 quantitative variables. So this is test 13, There's one population, two quantitative variables. A sociologist surveys 500 adults and records whether each person supports or opposes a proposed policy. The sociologist, 500 adults supports or opposes a proposed policy. The sociologist wants to compare the proportion of supporters between men and women. The proportion of supporters between men and women. Two populations, one proportion. So this one here is going to be test 4. So this has two populations, and it's a proportion, comparing proportions. That's all test 4 is. A nutritionist wants to know whether the distribution, I'm thinking this is a chi-squared test, which we will recall is from test, 9, 10, 11, or 12. Okay, so it's a distribution. So you have breakfast choices, cereals, eggs, fruits, or no breakfast, 4 categories among college students, matches a previously published distribution. All right, so this is going to be test 10. Why? Because it's one population, one categorical variable, and there's an expected distribution. Six, each teacher wants to know whether students perform differently on a standardized test after completing a review workshop. Differently after completing. This one here sounds like test 9, what we call the matched pair test. What do we call it here exactly? The paired population means. So we've got two populations. I put that in quotes because it's really the same people, but it's after something has changed, and so you can look at it as being different. And this is mean, but they are related. Two populations that are related. Okay, two different teaching methods are used to separate two classes. In two separate classes. So it sounds like the test scores from both classes are recorded. Population standard deviations are known, and the instructor wants to test whether the mean scores differ between the two classes. All right, so this is a test. So I see here two populations, one quantitative variable, they want to find the mean. So this is going to be test, 5 through 8. But what about the population standard deviation? It says they're unknown. They're unknown. Okay, and it doesn't say that they're assuming them to be equal, so it is unknown, unequal. So that's test 8. A company wants to compare the average commute times, I'm already thinking about mean here, average commute time to employees who work remotely versus those who work on site. Large independent samples are independent samples, so it's not going to be test 9. Samples are taken from each group, and the population standard deviations are known but not assumed to be equal. Okay, you pause it. What do you think? All right, so since they are known but not assumed to be equal, I'm thinking this is going to be test 6, right? 5 through 8 are the mean ones, the two population means. 5 is known equal, 6 is known unequal. So this is 6, there's 2 populations, one quantitative variable, and we want the mean. And then we also have, what is this? This is sigma 1 equals, does not equal, sigma 1 does not equal sigma 2, but both are known. So that's test 3. That's test 6. So with test 8, we had sigma 1 is not equal to sigma 2, and both of them were not known. Okay. A market researcher records the preferred brand A, B, or C, and age group of 600 customers. These researchers want to determine whether brand preference is related to age group. Okay, what we have here, so this right here is going to be test 11. Why do I say test 11? This is a test for independence. We've got one population, two categorical variables. And we want to know, are they related? So that's going to be test 11. Okay, the last one is for you to do. Put the test down here. Okay, what did we do today? We introduced hypothesis testing. We talked about 14 different tests. 14, it was a lot. 14 different tests. And their corresponding scenarios. Then we practiced identifying the appropriate test. All right, and that was it. That was it. So it didn't seem to cover, it wasn't a ton of stuff. It was a ton of information. But it was all pretty much the same thing. You had these hypotheses tests, there was different scenarios, and we wanted to identify, we wanted to, match the scenario, the scenario to the appropriate test. All right, that's it. So we'll talk more about this in class.